Every spaceship you've ever seen in a movie is a death trap. We imagine them as high-tech containers, vehicles equipped with blinking control panels and massive engines, designed for the single purpose of moving people from one point to another across the dark. This vehicle mindset works perfectly for short missions. On the Apollo missions, the walls of the lunar module were thinner than a credit card. The crew could endure the cramped, fragile conditions because they knew the journey would end in a few days, and Earth was always close by. Even the International Space Station functions as a dependent outpost. It relies on a constant stream of massive cargo resupplies and hundreds of specialists on the ground monitoring every single pump and filter around the clock. If those missions stopped tomorrow, the crew would have to evacuate within weeks. For missions spanning generations, that umbilical cord is cut. The voyage requires a structure that performs the work of an entire world, rebuilding every service Earth provides for free inside a sealed metal shell. Aboard the International Space Station, the water recovery system captures 98% of all moisture from crew breath, sweat, and urine. This is a massive engineering achievement, developed over decades of testing, to turn waste into water cleaner than what comes out of your tap. But look at the mathematics of a closed loop. If you lose just 2% of your supply with every cycle, the deficit compounds. Without a planetary scale cycle to filter and replenish the supply, the water reserve vanishes. In deep space, where there is no resupply and no rain, 98% efficiency is a slow motion countdown. It is a delayed death sentence. Earth does an incomprehensible amount of invisible work to keep you alive. Beneath your feet, the planet filters your water and protects you from radiation. In deep space, every single one of these silent services must be mechanically manufactured. To replace gravity and prevent human bones from dissolving, the ship must take the shape of a colossal spinning drum. The structure needs a massive diameter to generate centripetal force without making the crew constantly motion sick. Replicating the oxygen cycle and the food chain requires megawatts of continuous electrical power. LED arrays must illuminate thousands of square meters of crops with precise chemical balancing, replacing the work of a global biosphere. All that power creates a cooling problem because the vacuum outside has no temperature. It has no particles to carry thermal energy away through conduction or convection. The only way to stop the ship from cooking the crew is to wrap the hull in massive, fragile radiator panels. These arrays must grow to thousands of square meters, silently dumping infrared radiation into the void to prevent internal heat from reaching lethal levels. Deep space engineering is the trade-off of Earth's vast, free ecological buffers for a fragile, interdependent mechanical web. We have already seen the danger of closing these loops. In 1991, an experiment called Biosphere 2 sealed 8 people inside a miniature version of Earth's ecosystems, contained within glass pyramids and geodesic domes. Within months, the experiment began to unravel. Oxygen levels plummeted to concentrations seen at the top of high mountains, leaving the crew fatigued and struggling to think clearly. The culprit was hidden in the building's own structure. The fresh concrete foundation was absorbing carbon dioxide, masking the fact that soil microbes were consuming the oxygen faster than the plants could replenish it. On a planet, a minor reaction in a foundation is meaningless. Inside a sealed volume, small imbalances accumulate. There is no planetary atmosphere to absorb the shock of a trace chemical reaction. Think of life support as an interconnected web. Agriculture needs water, water needs power, power creates heat, which must be rejected. A micrometeorite damages one radiator. The heat node fails and temperatures rise. As heat builds, humidity spikes. The food node destabilizes. That moisture triggers a fungal infection, which spreads aggressively through the growth chambers and wipes out the crops. Without plants to process the atmosphere, oxygen output crashes, carbon dioxide levels spike, and the entire system collapses into an unstoppable existential threat. Earth uses its massive oceans and atmosphere to buffer these errors. A spaceship has no buffers. A minor mechanical failure can mutate into a catastrophe in hours. A perfectly balanced mechanical web still leaves one piece of the puzzle unsolved: the human mind. There is a psychological weight to knowing that every breath, every sip of water, and every sensation of weight on your feet is manufactured. In deep space, you live with the permanent awareness that your existence depends on machines that could stop. Then there is the second generation. Unlike the founders, these people did not volunteer. They inherit a world where their labor is required to keep the air clean, trapped in a zero-margin maintenance job they were simply born into. If later generations lose the technical knowledge to repair the ship, or if they grow to resent the burden, the civilization will collapse from within. For a generation ship to succeed, its engineering must reach a counterintuitive goal. It must become boring. Boring means the systems are so reliable and deeply integrated that they are invisible. A child born in this habitat should not know the name of the atmospheric processor. They should just breathe and think about something else. True success looks like a normal life. It is the ability to have trivial arguments, to watch children play in the corridors, and to take tomorrow completely for granted. Humanity's greatest technological achievement is not crossing the void. It is building a machine so reliable that the people inside mistake it for the ground beneath their feet.